Alabama STEM Explorers is made possible by the generous support of the HudsonAlpha Institute for Biotechnology, Southern Research, solving the world's hardest problems, the Hawley Family Foundation, Alabama Works, Alabama STEM Council, Alabama Mathematics, Science, Technology, and Engineering Coalition, Alabama Math, Science, and Technology Initiative.
Hey Cruz, beautiful day outside, isn't it?
Oh, hey Tim. Yeah, it's great out here.
Yeah, nice, warm, beautiful sunlight. You know what? Did you forget to put the sunscreen on?
No, I just put some on earlier. Actually, can you tell me more about sunscreen and how it works?
Well, sure. Sunscreen does two things. It reflects the sunlight and it also absorbs the sun rays. So, you know what? I got the perfect idea. How about you stay out here and enjoy a little bit of some more of the sunlight? I go in and set up some experiments and you come in and join me later.
Okay, yeah, that sounds good.
All right, man.
Yeah. Hi, welcome to Alabama STEM Explorers. I'm Cruz and this is my good friend Tim.
Hi.
And we're at the University of South Alabama in Mobile. So, you were just about to tell me about UV rays.
Yeah, so we're going to talk about not just UV rays, we're going to talk about waves in general. So behind us, I have a system in which we can demonstrate how waves work. Now, what do you see?
Duct tape, sticks, and gummy bears.
So, actually, that is all you need in order to make a wave machine. Duct tape, skewers, and gummy bears.
This doesn't look like a machine.
Cool. So that is perfect, but we're gonna watch how it works. So just flick that in. Just give it a little flick.
Okay. Whoa.
What did you notice?
Energy flows through the sticks and the gummy bears.
So energy moves throughout this system. As it moves throughout the system, we saw that it went up and what?
Went down.
So what if you gave it a little bit more energy? What do you think would happen?
Bigger energy waves.
Pretty cool. Now we can explain that in a very different way by looking at it on a sheet of paper. And Cruz, if you come over here, this could help us see what we just saw in that demonstration. So as that wave went through the system, we noticed that it peaked, and at that peak we call it a crest. And down at the bottom, when it went down, that is also called the trough. Now, the distance in between that is called the wavelength. Now, the lower the frequency, the lower amount of energy that it has. The higher the frequency, the more energy the wave has. Now, do you think you could give that wave system a little bit more energy?
Sure. That's a lot.
That's a lot. And it's pretty cool, isn't it? And this is a simple way to explain how waves moves through a system.
So I understand rays, but what does that have to do with light?
All right, Cruz, so come on over here and we'll go a little bit deeper with the understanding. So I have an electromagnetic spectrum here. And on here, it has the full range of light. And it starts on this end from lower frequencies all the way to higher frequencies. What do you notice?
I noticed a radio, things that I've used before, like a microwave, light bulb. I've seen the sun.
Okay, so with this, we see how light travels in waves. But today we're going to focus on a little bit more on how light interacts or how it behaves. So we're going to clear this off and we're going to do a couple more activities to show how light behaves. All right. Now we're going to bring in, I have Neil who's going to bring in to talk about the science of reflection as we do our next experiment.
Hey Tim, hey Cruz.
Hey.
How are you guys?
We're doing all right.
So y'all been talking about the electromagnetic spectrum and visible light and those kinds of things?
Yes, and how waves interact.
Perfect. So what we're going to talk about now, all of these experiments are around this concept that all objects when light falls on them, we can shine light on them or just the light from the room. They do three things. They reflect light, they absorb light, and they transmit that light. And different objects transmit, absorb, and reflect in different ways. So why don't we actually start with reflect? So Cruz, you got up this morning and you got dressed, and I imagine you actually looked in something to check how you were, you know, did your hair look
I was
good?
gonna look,
What
yes.
did you look in?
A mirror.
That's right. And what did you see in that mirror?
Myself.
And how did you see yourself?
It was a reflection.
A reflection. So the light that was shining on you reflected off you and into the mirror and then reflected back so that you could see it. So mirrors have a really shiny surface. Usually it's silver or some other metal that the light reflects back on so that you actually can see yourself. If you've ever, I don't know, have you ever looked at yourself in the back of a spoon? It's not really clear, but it sort of reflects a little bit. A mirror is a much better reflection. So we're going to do an experiment that talks about how mirrors reflect light back. And we're going to use a laser pointer. Tim's got a laser pointer. Now, you want to be really careful when you're working with a laser pointer if you're going to do this at home. You never point a laser in anybody's eyes or at anybody's face. You always make sure you know where the direction of the laser is going. And we've got a mirror over here, and so Tim is going to point the laser at the mirror, and we're going to be able to see it reflect off. And we're going to start just the way it is, and then we're going to actually do something that I think will make it easier for us to visualize it. So Tim, if you'll grab that laser. Cruz, go ahead and grab that bag. That bag has some flour in it, but I want you just to hold it out of the way for a second. We're going to start without you doing anything at all.
Okay.
Tim, go ahead and turn the laser on and point it in the mirror. And we're going to make sure that we see where it is. Okay, move it over a little bit more. There we go. All right, so it's not pointing in anybody's eyes. Now, can you actually see the light? You can see the dot of light, but Cruz, can you see the actual beam of the laser light?
No.
No, and you can't see that it's reflected either, can you? So we're going to add some flour over the surface to be able to capture the beams of light so we can see it and see how it's reflected. So I want you to grab that bag, and I want you to clap. And as you clap with that bag, we're going to get little bits of flour everywhere.
Okay.
Careful, guys. You're not going to want to breathe in too deeply, or we're going to get lungs full of flour. Okay? Go ahead and start clapping. Okay, you want to cover the whole area. Okay, so what we're seeing is we're beginning to see the flour is catching the laser light, and we're actually able to see the beam of light going towards the mirror and then reflecting off, bouncing back in a different direction. Yeah.
Wow, that's really good.
Yeah, you can actually see that, whew, there's a nice big cloud of flour in here. It looks like we've been baking cookies. All right. Okay, so there's our first point, reflection. So light reflects off. Light reflects off all things, but mirrors are designed in such a way that it reflects almost a perfect image back from you. All right, let's clear this table and we'll move on to the next part of what light does and doesn't do.
All right.
For our next activity, guys, let's talk about colors. Now, tell me, when you go to the closet in the morning and you've got all your clothes, do you go for the more colorful clothes, or are you going for more of the, not so colorful? Cruz?
Well, I would say more in the middle, not too colorful, but not too bland.
So is this red lab coat kind of in your style, or is this way too bright for you?
It's a little too bright.
It's a little too bright, fair enough. Tim, how about you? Are you a bright color guy or not so much?
I like the colors.
So you're actually kind of in a not such a bright color. So maybe we should have had you guys switch lab coats. Not that we'll do that right now. But, okay. So let's talk about what allows us to see colors. And to do that, we first have to split light. Have you ever split light before?
No, I haven't.
That sounds like it might be kind of painful, doesn't it? But it's really not. Visible light, the light that comes from the sun, from the light bulbs, from a flashlight, is made up of all different wavelengths of colored light. And we can split it into its individual colors if we have something called a prism. A prism is made of quartz or sometimes of glass, and it bends light and it bends it out into its colors. But we actually can do this with stuff that you guys probably have at home as well. All you need is a glass that's got water in it and a flashlight. So, Cruz, we're going to actually shift this right to the edge of this table, and I'm going to try really hard not to knock it over. And I'm going to have you turn the flashlight on, And you're going to need to hold this in some different places. And what
Okay.
we're looking for on the floor, there's a piece of paper on the ground. We're looking to be able to see a rainbow. All right, so let's see what you can get. You may have to move it around some. If you're trying this at home, you want to get your flashlight right at the level of where the water is in the glass, and you want to point through the glass and through the other side.
Wow, Cruz, that looks really nice.
Yeah, we're beginning to see that rainbow. What colors can you see
I can
there?
see red, orange, yellow, basically all colors of the rainbow.
That's right. That's right. So visible light is split into what's called Roy G. Biv. Each one of those letters stands for the first letter in one of those colors. Red, orange, yellow, green, blue, indigo, and violet. What you're doing is you are actually bending the light as it passes through the water and through the glass and separating out each of those wavelengths. Okay, go ahead and turn that off and let's pull this back a notch. Now, I've got a whole bunch of colored fabrics in front of us. When color occurs when certain wavelengths of that light are reflected back to our eyes. So for example, red fabric absorbs every color except red, and it bounces red back, and so that's what your eyes see.
Yes.
So what do you think happens with blue fabric?
Shines off blue.
Yeah, it reflects back off blue, absorbs everything else. Green reflects back off. How about black? What do you think happens with black?
Well, I don't know. There's really not a color of light that's black.
No, there's not. Tim, any sense what's going on here?
I think it just absorbs all of the color.
That's exactly right. Black fabric absorbs every single one of the colors. Nothing reflects back. And so, what do you think happens with white fabric?
It reflects off more.
It reflects every color back. And so you aren't absorbing any of those individual spectra. Now, we can actually see that with another activity with gummy bears. I know you guys did a gummy bear wave machine earlier, so we brought some gummy bears back for everybody to look at. We've got red gummy bears and we've got green gummy bears. And we've got two different laser pointers. Now, again, you want to be really careful where you point these lasers, that you're not pointing them in people's eyes. But we've got a green laser and we've got a red laser. And those lasers only show that wavelength of light. So we don't have any of the other wavelengths. They only create wavelengths that are the specific red or green. I'm going to swap these around, and I want you each to turn on your laser pointer, and I want you to shine them through the red or the green gummy bears.
Okay.
All right? Okay, when you do that, Cruz, you might need to move yours a little closer to the gummy bears. Are you seeing light? Well, you tell me, what are you seeing? What's the behavior of
It's
light?
traveling through because it's the same color.
Yeah, it's traveling all the way through. It's the same wavelength, and it's not being absorbed. It's being reflected. It's being spread across. And the same, it really shows up with Tim. Tim has a much stronger laser, a red laser, and so it's moving through all the gummy bears, unlike the green, it's just only going through a few. Now, swap laser pointers, guys. Let's see what happens now when you actually are trying to shine a certain wavelength of light against something that doesn't reflect that back.
Wow.
What are you getting?
See, it's absorbing the
Yeah.
light.
Yeah.
It's absorbing. It's not passing through because it's now being absorbed by the green light is being absorbed by the red gummy bears, and the red light's being absorbed by the green gummy bears. Okay. All right. We've now talked about how light is reflected with a mirror. We've talked about how light is absorbed and bounced back for us to see colors and to split out light. Now let's talk about one more piece, and that's going to be how light is transmitted, but how it sometimes is transmitted at a different angle. So for that, we've got to reset one more time for one more set of experiments. All right, this is our last activity about light, guys, and let me start with a question. Have either of you ever been spear fishing?
I haven't.
You have not, Tim?
No.
I had a chance to once in the Bahamas, so.
So did you actually get to spear a fish?
No, I didn't get a chance to spear the fish, but I did get a chance to see someone spear a fish.
All right, we're going to circle back to spear fishing. If you're wondering how this relates to light, I promise we're going to make the connection. The last principle we're going to talk about is how light actually bends or refracts as it moves through different kinds of materials, different surfaces. So we're going to start. Cruz, we've got a straw right here. Just put that straw in the glass. This is something you can definitely do at home. You just need a clear glass, fill it with water, and then put a plastic straw in. Okay, now we're going to come down at eye level and we're going to look at the straw. When you look right at the level where the water is, it looks like the straw is broken, doesn't it?
Yes.
Yeah, the two pieces look like they don't fit. But it's clearly all one straw. So we can come back up. The issue here is that when light moves through the air, it moves at one speed. But when it moves into water, it slows down. The speed changes, and so the angle, the wavelength of the light changes direction a little bit. And that changing of direction as it comes back, as our eyes capture that, our eyes can't process how this is one place and this is another, and so it looks like it's broken. Now, that ties back to spearfishing, because if you are looking through the water trying to spear a fish, where you think the fish is not, because of the changing of the light waves. You have to spear where the fish is, not where your eye tells you that it is.
So our eyes play tricks on us?
Our eyes play tricks on us. They play tricks on us all the time. And here's one more trick that we're going to talk about. We're going to make something invisible.
Okay. How do you do that?
Yeah, again, it's going to be a trick with our eyes.
Okay.
So remember, when you look at something, the light that reflects back has passed through, like this glass test tube, it's passed through the glass and then through the air and back. So it has it has refraction and it has reflection. Go on ahead and take this test tube and drop it in that container of water. Okay, can you see it?
Yes, I can.
Okay, you can see, because as we're looking through the water, we can see the glass, because the glass has a different reflection and refraction than the water. And so that's why you can see the outline of it. Okay, Tim, thank you very much. Now we're going to take this test tube. Go ahead and set it down here.
Okay.
Cruz, pick that one up and put it into this vial. This is cooking oil. So put it in and let's wait and see. Let's see what happens.
What?
Can you see it?
Barely. I can see the logo, but
Yeah, but that's
nothing
it.
else.
So cooking oil, vegetable oil, has the same properties as that glass test tube. And so when you put an object inside another object that has the same optical properties, that light moves in the same way, it makes the first object invisible. It's still there, but it's a trick of our eyes. So scientists are actually trying to figure out how to create true material that has the same properties of light. It reflects back light just like the air around it. And if they can figure out how to do that, then they've actually created an invisibility cloak.
So we just went back to Harry Potter and brought us back to our experiment. It's pretty cool. Now, Neil, what about the people at home, the kids who are going to go inside the cabinets and grab all their mom's cooking oil?
Yeah, yeah. So this is an activity that you really want to make sure that somebody at home, a guardian, is working with you on before you start opening up cans of liquid and pouring them into containers. This is messy. We've all got greasy fingers right now. And some objects, I've shown you a glass test tube. It's made of Pyrex. Pyrex has the same property as cooking oil, but if you just picked up a piece of glass from your house and put it in, it wouldn't necessarily become invisible. You've got to know the principles and properties. So yeah, you can definitely do the straw in the water at home. Ask a guardian before you actually start trying to look for things that are invisible. So gentlemen, we've now talked about multiple different properties of light. That light behaves as a wave of energy, that visible light is part of the electromagnetic spectrum, and what makes light visible versus ultraviolet and infrared is the wavelength of that, so the distance from one crest to the next. And then we've talked about different properties of materials that reflect or absorb or refract light in different ways. Everything around us we see because of light that falls on it. But now we've got a better sense of how our eyes see it and how that light behaves. It's a pretty cool process, isn't it?
So now our eyes can't play tricks on us.
Or at least we know that they're playing tricks on us.
Hi, my name is Anjana, and I was wondering, what makes a rainbow, and why is it curved?
So how many times have you gone to the end of the rainbow looking for that pot of gold? We've all marveled at the beauty of a rainbow. Rainbows are formed when sunlight is refracted by water droplets into the atmosphere. A rainbow is caused by sunlight and atmospheric conditions. Light enters a water droplet, slowing down and bending as it goes from air to denser water. And then that same light reflects off the inside of the droplet, separating into components known as wavelengths or colors. Sunlight is actually a band of waves of different colors with different wavelengths. Sometimes the colors are referred to as Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. And when that light exits that droplet, it makes a beautiful rainbow. A rainbow is curved because the water droplet that produced the rainbow forms an arc. A set of all the raindrops that have the right angle between the observer, the drop, and the sun lie on a cone pointed at the sun with the observer at the tip. The reflection of all the water droplets look like a cone from the observer's eye. Ooh, I love to find the gold at the end of the rainbow.
What got me excited into space was an internship. And so I interned at Boeing in Huntsville, and I also interned at Alabama Power during my sophomore and junior years in college. And based on those internships, I got a chance to see what it was like working at a power company, which was in Birmingham, and then coming here to work in this factory as an intern. But based on those internships, I was really excited about the marvelous things we were doing here in space, and the internship is what sold me. Some of the STEM things I use here every day at work: science, technology, engineering, and math. I get to work a lot with some marvelous people, technicians, people in procurement, finance, you name it. So sometimes when we think STEM, we only think you have to be an engineer to work at this marvelous rocket company. That's all but true. We have various fields here, and when I go out and volunteer and speak to kids at school, I also talk about my engineering experience here, but I also give a background of different careers and opportunities that we do have here at ULA. There's a t-shirt that I like to wear, and it says, "Math is hard, so is life. Get over it." So don't let math or science or technology scare you, because growing up as a young kid, I didn't have a lot of opportunities being in an underprivileged environment. So I tell any kid that's out there, follow your dreams and follow your passions. And no matter how hard it gets, hang in there and keep going. And you know, there's nothing wrong with saying, I need help, I need tutoring, what have you. If it's your dream, if it's your passion, please speak up to a teacher, somebody that mentors you, that comes in to speak, like myself. There are tons of people out here willing and ready to help, but we just have to know that that's something that you want to pursue, and you have all of the resources that are available to you.
Watching Alabama STEM Explorers. If you missed anything or you want to watch something again, you can check out our website at alabamastemexplorers.org. Maybe you have a question we could answer here on the show, and you might grab a cool t-shirt. Feel free to send us a video question or an email on our website, alabamastemexplorers.org. Thanks again for watching. We'll be back next week.
Alabama STEM Explorers is made possible by the generous support of the HudsonAlpha Institute for Biotechnology, translating the power of genomics into real-world results. Southern Research, solving the world's hardest problems. The Hawley Family Foundation, established to honor the legacy of Brigadier General Everett Hawley and his parents, Evelyn and Fred Hawley, champions of servant leadership. Alabama Works, a network of interconnected providers connecting business and industry needs to a highly skilled and trained workforce. Alabama STEM Council, dedicated to improving STEM education, career awareness, and workforce development across Alabama. Alabama Mathematics, Science, Technology, and Engineering Coalition for Education, advocating for exceptional STEM education in Alabama. Alabama Math, Science, and Technology Initiative, the Alabama Department of Education's initiative to improve math and science teaching statewide.